So this triangle symbol stands for the capital Greek letter delta, and then H, capital H, does stand for enthalpy, but I'm just going to refer to it as capital H. So delta H1 is the breaking of solvent-solvent intermolecular forces, so the solute can diffuse through the solvent. Delta H2, breaking of the solute-solute intermolecular forces, so the solute can diffuse through the solvent. Delta H3, formation of the solute-solvent intermolecular forces, and then this word here, than, is a typo. It should be changed to that, enable dissolving, if you could do that in the transcript. Delta H1 plus delta H2 plus delta H3 equals enthalpy of forming a solution. Capital S subscript G is equal to K multiplied by capital P subscript G, where capital S subscript G is the solubility of the gas, lowercase k is the constant that depends on the gas, capital P lowercase g is the partial pressure of the gas on the solution. Unit, lowercase m capital M, or millimolarity, 1 times 10 to the negative 3 moles per liter, due to low solubility. These are calculated in the same way as percentages, mass of the solute divided by mass of the solution, and multiplied by 1 times 10 to the 6, which is 1 million, or 1 times 10 to the 9th, which is 1 billion, respectively. And then as I'm looking at Raoult's law here, there's something that I would like to change as well. In what you have here, which I am expecting is the same as in the original transcript, I just have capital P solvent in solution. I'd like you to add this piece here that is highlighted is equal to capital P subscript solution. So that capital P is going to be the vapor pressure of the solution. Okay, so the pressure of the solvent which is in solution, let me just put this which here to clarify. I didn't mean to make it that big. Okay, so if you could just add what is in yellow here. So vapor pressure of the solvent which is in solution is the vapor pressure of the solution is equal to chi of the solvent times the vapor pressure of the pure solvent. So here this X looking thing is actually the Greek letter chi. P here is going to be vapor pressure of the solution, and P with this degree symbol here is vapor pressure of the pure solvent. And this little degree symbol here is highlighted. I'm not sure why it was missing, but this degree symbol should be next to this capital P because it distinguishes it from this P. This P with the degree symbol is the vapor pressure of the pure solvent, and over here this is the vapor pressure of the solution. Colligative properties. Van't Hoff factor I. For NaCl or sodium chloride, and you are more than welcome to add that into the transcript, it would be 2, since 2 moles of particle, Na plus and Cl minus, form for each mole of NaCl. For CaCl2, or calcium chloride, and again, that can be added directly into the transcript, it would be 3. And you know, it might be better, hold on a second. Okay, so this is a lowercase I, and it needs to be a lowercase I. I don't have time to fool with it. It's coming as a capital I here. But I think perhaps it would be better in this transcript to refer to the Van Hoff factor instead of it as the actual lowercase I. So for sodium chloride, the Van Hoff factor I would be 2, since 2 moles of particles, Na plus and Cl minus, form for each mole of NaCl. For CaCl2 or calcium chloride, I would be 3, since 1 mole of CaCl2 forms 3 moles of particles when dissolved, 1 mole of Ca plus 2, and 2 moles of Cl minus. Okay, so here we have this delta again. Delta T is equal to I K subscript B lowercase m. Delta T is the increase in temperature of the boiling point. Lowercase k subscript b is the constant which depends on the solvent. Lowercase m is the molality of the solute. And lowercase I is the Van Hoff constant. For non-electrolytes, I is equal to 1. Delta T is I, lowercase k subscript f, lowercase m, where delta T is the change in temperature from the melting point of the solvent. Okay, so hold on. I should really clarify this. It's not just change in temperature. If you would, we could change this to decrease in temperature. And I'll highlight that so it's easy to find. So delta T is the decrease in temperature from the melting point of the solvent. Lowercase k subscript f is the constant that depends on the solvent. Lowercase m is the molality of the solute. I is the Van Hoff constant. For a non-electrolyte, I is equal to 1. And I notice that I has not been italicized. It probably should, it needs to be italicized throughout the transcript for consistency. So it's not italicized here, it should be italicized. Can't remember if I said this. For a non-electrolyte, I is equal to 1. Once delta T is calculated, subtract it from the melting point of the solvent. Capital P is equal to lowercase I, capital M, RT, where capital P is osmotic pressure, I is the Van Hoff factor, capital M is molarity of the solution, and maybe we should remind our students what that is. Moles of solute per liters of solution. So I think that might be a good thing to add, even though they should probably know it. I think it doesn't help to add that. Capital R is the gas constant of 0.0821 atmosphere liters divided by mole K, and capital T is the temperature in units of Kelvin.